In mathematics and abstract algebra, a relation algebra is a residuated Boolean algebra expanded with an involution called converse, a unary operation. The motivating example of a relation algebra is the algebra 2x squared of all binary relations on a set X, that is, subsets of the Cartesian square x2, with Rs interpreted as the usual composition of binary relations R and S, and with the converse of R interpreted as the inverse relation. Relation algebra emerged in the 19th century work of Augustus de Morgan and Charles Peirce, which culminated in the algebraic logic of Ernst Schroeder. The equational form of relation algebra treated here was developed by Alfred Tarski and his students, starting in the 1940s. Tarski and Givant applied relation algebra to a variable-free treatment of axiomatic set theory, with the implication that mathematics founded on set theory could itself be conducted without variables. Definition: a relation algebra is an algebraic structure equipped with the Boolean operations of conjunction xy, disjunction xy, and negation x-. The Boolean constants 0 and 1, the relational operations of composition xy and converse x, and the relational constant I, such that these operations and constants satisfy certain equations constituting an axiomatization of relation algebras. A relation algebra is to a system of binary relations on a set containing the empty, complete, and identity relations enclosed under these five operations as a group is to a system of permutations of a set containing the identity permutation, enclosed under composition in inverse. Following Johnson and Xenakis, it is convenient to define additional operations xy equals xy, and, dually, xy equals xy. Johnson and Xenakis showed that Ix equals xi, and that both were equal to x. Hence a relation algebra can equally well be defined as an algebraic structure. The advantage of this signature over the usual one is that a relation algebra can then be defined in full simply as a residuated Boolean algebra for which Ix is an involution, that is, I equals x. The latter condition can be thought of as the relational counterpart of the equation 1 equals x for ordinary arithmetic reciprocal, and some authors use reciprocal as a synonym for converse. Since residuated Boolean algebras are axiomatized with finitely many identities, so are relation algebras. Hence the latter form a variety, the variety Ra of relation algebras. Expanding the above definition as equations yields the following finite axiomatization. Axioms: the axioms B1, B10 below are adapted from Givant, and were first set out by Tarski in 1948. L is a Boolean algebra under binary disjunction, and unary complementation equals CB3 equals A. This axiomatization of Boolean algebra is due to Huntington. Note that the meat of the implied Boolean algebra is not the operator, nor is the one of the Boolean algebra the I constant. L is a monoid under binary composition and nullary identity I. B4 equals CB5. AI equals a unary converse equals BA. Axiom B6 defines conversion as an involution, whereas B7 expresses the anti-distributive property of conversion relative to composition. Converse and composition distribute over disjunction. B8 equals ABB9. C equals B10 is Tarski's equational form of the fact, discovered by Augustus de Morgan, that ABC minus ACB minus CBA minus B10 minus B minus equals B minus. These axioms are ZFC theorems for the purely Boolean B1, B3. This fact is trivial. After each of the following axioms is shown the number of the corresponding theorem in CHPT. 3 of Suppus, an exposition of ZFC. B427, B545, B614, B726, B816, B923, expressing properties of binary relations in Ra. The following table shows how many of the usual properties of binary relations can be expressed as succinct Ra equalities or inequalities. Below, an inequality of the form AB is shorthand for the Boolean equation AB equals B. The most complete set of results of this nature is CHPT, C of Carnap, where the notation is rather distant from that of this entry. CHPT 3.2 of Suppus contains fewer results, presented as ZFC theorems and using a notation that more resembles that of this entry. Neither Carnap nor Suppus formulated their results using the RA of this entry, or in an equational manner. Expressive power. The meta-mathematics of RA are discussed at length in Tashi and Givant, and more briefly in Givant. RA consists entirely of equations manipulated using nothing more than uniform replacement and the substitution of equals for equals. Both rules are wholly familiar from school mathematics and from abstract algebra generally. Hence RA proofs are carried out in a manner familiar to all mathematicians, unlike the case in mathematical logic generally. RA can express any first-order logic formulas containing no more than 3 variables. Surprisingly, this fragment of FOL suffices to express Peano arithmetic and almost all axiomatic set theories ever proposed. Hence RA is, in effect, a way of algebraizing nearly all mathematics, while dispensing with FOL and its connectives, quantifiers, turnstiles, and modus ponens. Because RA can express Peano arithmetic and set theory, Gödel's incompleteness theorems apply to it. RA is incomplete, incompletable, and undecidable. The representable relation algebras, forming the class RRA, are those relation algebras isomorphic to some relation algebra consisting of binary relations on some set, and closed under the intended interpretation of the RA operations. It is easily shown, e.g., using the method of pseudo-elementary classes, that RRA is a quasi-variety, that is, axiomatizable by a universal Horn theory. In 1950, Roger Linden proved the existence of equations holding in RRA that did not hold in Rath. Hence the variety generated by RRA is a proper subvariety of the variety Rath. In 1955, Alfred Tarski showed that RRA is itself a variety. In 1964, Donald Monk showed that RRA has no finite axiomatization, unlike RA, which is finitely axiomatized by definition. Q-relation algebras and RA is a Q-relation algebra if, in addition to B1 B10, there exists some A and B such that Q0, AAI Q1, BBI Q2, ABE equals 1. Essentially, these axioms imply that the universe has a pairing relation whose projections are A and B. It is a theorem that every QRA is a RRA. Every QRA is representable. That not every relation algebra is representable is a fundamental way RA differs from QRA and Boolean algebras, which, by Stone's representation theorem for Boolean algebras, are always representable as sets of subsets of some set, close under union, intersection, and complement. Examples. 1. Any Boolean algebra can be turned into a RA by interpreting conjunction as composition, i.e., xy is defined as xy. This interpretation requires that converse interpret identity, and that both residuals y, x and x, y interpret the conditional yx. 2. The motivating example of a relation algebra depends on the definition of a binary relation R on a set X as any subset Rx squared, where x squared is the Cartesian square of X. The power set 2x squared consisting of all binary relations on X is a Boolean algebra, while 2x squared can be made a relation algebra by taking Rs equals Rs, as per example above. The standard interpretation of is instead xz equals y, xrysz. That is, the ordered pair belongs to the relation Rs just when there exists yx such that R and S. This interpretation uniquely determines R(S) as consisting of all pairs such that for all xx, if x are y then xsz. Dually, S(R) consists of all pairs such that for all zx, if y are z then xsz. The translation equals then establishes the converse R of R as consisting of all pairs such that R. 3. An important generalization of the previous example is the power set 2e, where ex squared is any equivalence relation on the set X. This is a generalization because x squared is itself an equivalence relation, namely the complete relation consisting of all pairs. While 2e is not a subalgebra of 2x squared when ex squared, it is nevertheless turned into a relation algebra using the same definitions of the operations. Its importance resides in the definition of a representable relation algebra as any relation algebra isomorphic to a subalgebra of the relation algebra 2e for some equivalence relation E on some set. The previous section says more about the relevant meta-mathematics. 4. If group sum or product interprets composition, group inverse interprets converse, group identity interprets psi, and if R is a one-to-one correspondence, so that RR equals I, then L is a group as well as a monoid. B4, B7 become well-known theorems of group theory, so that RA becomes a proper extension of group theory as well as of Boolean algebra. Historical remarks. De Morgan founded RA in 1860, but C.S. Peirce took it much further and became fascinated with its philosophical power. The work of De Morgan and Peirce came to be known mainly in the extended and definitive form Ernst Schroeder gave it in Volume 3 of his Vorlesungen. Principia Mathematica drew strongly on Schroeder's Ra, but acknowledged him only as the inventor of the notation. In 1912, Alwyn Cosset proved that a particular formula in which the quantifiers were nested 4 deep had no Ra equivalent. This fact led to a loss of interest in Ra until Tashi began writing about it. His students have continued to develop Ra down to the present day. Tashi returned to Ra in the 1970s with the help of Stephen Givant. This collaboration resulted in the monograph by Tashi and Givant, the definitive reference for this subject. For more on the history of Ra, see Maddox. Software. Real mix. Relational methods in computer science maintained by Wolfram Karl, Carsten Sins, Ara, and automatic theorem prover for relation algebras.